Hello, welcome to Engineer's Edge gd&T applications. What we're going to do is show you a refinement of orientation by using a parallelism. And the illustration we have is a simple connecting rod as might be used within your reciprocating engine in your car, scooter, motorcycle. And the large lower diameter has been identified as a datum feature. It has some diameter d sub 1 plus or minus 2. And we have located the upper diameter, which is specified as a diameter of d sub 2 plus or minus 2 thousandths, with a dimension origin. And the dimension origin is indicating that we will measure from the lower hole to the upper hole to some distance y sub 1 plus or minus 10 thousandths. So what that distance dimension does give us is two tolerance planes that are as deep into the screen, if you will, as our upper hole feature is long, and this allows our as-built hole feature to perhaps start at the closest distance and then tilt away from our lower diameter d sub 1 by up to that plus or minus 10, which is a total worst case parallelism of 20 thousandths. So to refine this parallelism, we're going to associate our feature control frame with our size dimension, and we're going to use a orientation control. We're going to use angularity, but as we know, parallelism is equal to angularity. I'm going to assign a parallelism of 2 thousandths relative to datum A. So this creates two parallel tolerance boundaries that are, by the way, contained within the limits of size tolerance, and they're parallel to our datum axes A. Another approach is shown in this view, where we have actually used a position tolerance to control the distance between our datum feature d sub 1 and our upper hole feature d sub 2. And here we have a positional tolerance, diametric tolerance boundary of 20 thousandths, that regardless of feature size, relative to our specified datum A. Please do note that our dimension is a basic dimension, or a TED if you're an ISO individual. But in this particular case, what we have is a diametric tolerance boundary that's located at that basic dimension distance from our datum feature A. That tolerance boundary is diametric. It is diametric by 20 thousandths, and the length is equal to whatever length that as-built hole d sub 2 is. So what this does say to us is that our as-built hole feature d sub 2 could be drilled such that the start hole is at one end of our diameter, 20 thousandths diameter, and then as we drill through the material, that our as-built hole axes deviates throughout that 20 thousandths. So this isn't good enough. We want to refine this parallelism And in this case, what I'm going to simply do is associate my feature control frame with my size dimension. Again, I'm going to use the angularity symbology since we know it's the same as our parallelism. I am going to specify my tolerance boundary to be diametric. Again, my 2000s tolerance relative to A. This is a separate requirement. So what this gives me is two tolerance boundaries. First, I have my 20,000s tolerance boundary given by my position tolerance. And then I'm going to have a smaller tolerance boundary. It is parallel to my specified datum A. It is equal to a diameter of 2000s regardless of feature size. The distance is not specified because this is a parallelism. So the axes of the as-built whole D sub 2 must fall within the positional tolerance of a diameter of 20,000 RFS relative to A, in addition to being refined more parallel to our datum A within a tolerance boundary of 2000s relative to A. Thank you for watching.